that talk by Andrzej Hryczuk from NCBJ. He's currently now here in the University of Warsaw in NCBJ. Before he was at CISA, where he did his PhD. And he's been working on Munich. Can you hear me on Zoom? Hope that is it. And then he also started work in the University of Oslo. So that's part of his trajectory. Hope I didn't omit much of it. And today he's going to be talking about particle dark matter nature of your organisms. We're happy here. Thank you.
Thank you very much.
Yes, of course.
Thank you for the introduction, for the presentation. I'm happy to show a few examples on dark matter, and then in the last part, some of my results. But my main focus is to give a review. As much as I understand, most of you don't work in the field, not even in particle physics nor cosmology. So I'll try to say some interesting things that you probably haven't heard that much in general talks about. Okay, and then in the second part, I will talk about some results that we will try to with people. I apologize if the slides are pretty small, so if there is something with a small font that you want to read, just let me know. Perhaps also can interrupt me with questions anytime. Okay, so the outline of my talk is, as I said, first I want to recap a bit of evidence to propose the expectations about dark matter. Dark matter status around 2025, and then some first introduction and then introductions to dark matter. So let me start with a very generic kind of philosophical question. In the part, so as a practical part, do we see everything there is? And the answer to this is obviously no. Our eyes don't evolve to see everything, we don't see many gases. And in fact, if you look in space, you also won't see most of the mass, which is gas. And also, as the topic says, we don't see dark matter. But my philosophical question is more like, should we really expect to see? If you come back 100 years ago when particle physics said that we have electron and proton, this was really surprising that there is some other form of matter. But nowadays, much more elaborate particle physics, I don't think we really have a good answer to the question, should we expect? I don't think we have a strong evidence or way of thinking that dark matter is really a surprise, or actually it should have been a posteriori should be predicted if we know the particle physics well enough. If you look at the history of dark matter, it's actually quite an interesting interwoven those two themes of should we expect or not dark matter. And I suggest a great bit of Berton and Kutler wrote a history of dark matter paper, and then they made this point that the idea, well, which is quite known, the idea of dark matter, that some dark matter exists in the universe, is a very, very old idea, and in fact goes back to Lord Kelvin and even earlier. But most of the part of this history is that dark was understood as an adjective. So basically, you expected normal matter, but just can't say it. But then, even establishing the rotation curves of galaxies that are flat at the high radii, people not really establish the fact that it's a new kind of matter. People still thought that probably it's more like some unseen gas or compact objects, rather things like this. So the question is what made it transfer the proper now? The dark matter as being something just different. And indeed, what I would like to say is that rotation curves are as commonly seen as the kind of simplest evidence for dark matter, but this frames the issue as an astrophysical one. As we look at the universe, we don't see something, we see an effect of mass, we don't know what it is. But in fact, from physics or cosmology, the more robust evidences are more from CTP anisotropies, matter power spectrum, and also from an independent measure of baryons from VPN. And those evidence tell us that dark matter is indeed a different form of matter. It's not baryonic. If it were baryonic, this would not fit the cosmic way CTP anisotropies, or VPN would not work this way. And of course, there is also the famous bullet cluster as an evidence, where I don't don't think I need to explain too much, but the main point here is that the traces of the mass with the light coming from lensing as a green contours do not overlap with the hot gas observations from X-rays. In fact, this is the most famous one, but there are at least 72 similar systems, which together give more than 70 evidence. First question, ready?
It's just a short comment, Andrzej.
Yes.
I really appreciate that because I think you're a background in particle physics. That indeed, whenever people talk about dark matter and astrophysics, we have a very big error bars. So particle physicists never took it seriously. But it's mainly worth noting and repeating out loud that just CMB alone is 40 sigma detection of non-baryonic dark matter. So
Yes,
it's very strong evidence.
Yes, so that's why, like, the astrophysics perspective is a bit different than what we have, and for me, it's also closer to what I'm saying. All right. So to summarize a bit, so there's plenty of evidence on astrophysical and cosmological scales that dark matter or something like dark matter exists. From rotation curves, from galaxy-galaxy lensing, from velocity dissipations and X-ray observations, colliding galaxy clusters like the Punnett cluster, large-scale structure formation, the cosmic shear and CMB lensing, and acoustic peaks. And this gives a qualitative convergent picture, as all of you know very well. But there's no direct evidence that it's particle. Which you want to evaluate, find particle dark matter. But from my side, we want to first kind of have an idea what particle dark matter is consistent with particle physics, what is how useful it is for understanding other aspects of particle physics.
What's the alternative? You say it's not the evidence of particle.
Yeah, so
what else could it be?
So there are, okay, the better option for me would be primary black holes. And primary black holes are not a bad dark matter candidate, except that they're hard to produce. In a sense, you have the standard cosmology, you would require very high perturbation densities to get primary black holes produced in right quantities, which is possible, but just not an extrapolation of numbers. And also there are unique microlensing limits, so it's not every primary black hole would be allowed. And there's only small mass window, like small in terms of like the whole mass window, but still in terms of the actual value, large mass window. But also some people working with modification of gravity, which is a completely different story, which I think is interesting, but maybe not that much promising in actually addressing this. Okay, so my perspective is from particle physics, and so let's kind of do a thought experiment. Let's ask this question. So if we knew nothing about particle physics cosmology whatsoever, what would we say? And this is this idea of how much can be expected. In this review, they had a very nice kind of thought experiment in a way. So imagine you know quantum mechanics and nothing else, and then you look at what is in the universe on like large scales, from hydrogen atom molecules, viruses, humans, and sun, stars, etc. And you can see that they very roughly go on trajectory where normal matter with the density of matter, like mass over the size, behave as the mass mostly is a proton divided by the size was the red atom size, and then you get that's like 4th power of the mass scale. And then you can see a nuclear matter, which goes on a similar trajectory, but then also power but different mass to power 4. And then if you extrapolate this to lowest possible, like quantum mechanics, lowest possible size, you would kind of very, very roughly, but hit on an actual measured proton mass and actual measured electron mass. So you could play this game, so you can say, okay, we do expect from what we just see, stable particles of this type of masses. But then we also have observations from astrophysics of star clusters, dwarf galaxies, etc. Those systems which are dominated by dark matter. So what we play the same game, we just extrapolate. Now, admittedly, many orders of magnitude, we'll end up somewhere here and dark matter like particle physics type of a mass. And it can be orders of magnitude up and down, but like this is not 10 to the 15 GeV, this is not from other black holes, this would be kind of like in the particle physics range. So it's an interesting kind of thought experiment, but the point I want to make here is that you do expect indeed some particle with a mass from all those observations. So why not? Like we could text receive this kind of mass. Okay, and standard model. So this is particle physics perspective. I need to say something about standard model. So all of you know that standard model of particle physics is a great theory, as Hryczuk called coined the term the core theory of standard model plus general relativity, and this basically explains, at least fundamentally, most of the stuff we can observe. But the funny thing about standard model is that when you look here, you have those two particles which kind of together like essentially everything, but we have many more particles. And as I said at the beginning, if you were 100 years ago, if all those particles would know, you would be really surprised if I told you that there are actually many more states. And one of the particles that needed, the famous words of Fizyki, who ordered all of that, and this was actually in 36 after the muon discovery, not after all of this. Right? So from particle physics perspective, we now know that there are many more states than actually we see by just observing the stuff around us. So in this sense, I would say it's not very surprising that there's some perhaps additional states which just are in this space much more less densely distributed. And in fact, we do know that standard model has problems, and those problems are typically down to search for in physics. And those problems are both cosmological in nature, like purely theoretical organization of gravity, or as Andrews would like to say, gravitizing quantum mechanics. But also there are problems just through particle physics. So first of all, the neutrino have masses, and there are only some model. This can be unrelated very easily, but still. There are noise oscillations still. There are Cargill type problems for Higgs mass, most famous, but also strong CP and cosmological constant problems. And some unification, proton decay problem, but stable, neutron decay lifetime, etc. So what I want to say is that we know from this that standard model is not complete. Its extension in principle could be rather minimal in many aspects, but it's far more likely there are many states, many new states we don't know yet. And in particular, for example, if you want to have biogenesis and satisfy Sakharov conditions, you know, to have CP validation, all states that actually allow you to have CP phases in your Lagrangian. So you expect more than just one state typically to actually explain even those problems, not to mention also like quantization of gravity. It's pretty clear, for example, that give you a lot of states in the spectrum. Okay, so but if there are new particles, then it's quite possible that some of them are a dark matter. Like even neutrinos are a form of dark matter, a small amount of dark matter is in neutrinos. So the only real question is, as long as they are stable. Most of those states, which we discovered after the 1960s, are unstable, they just decay. So this is kind of for me the main point here. But if they are, it would be natural to expect that they actually are the dark. So from my point of view, particle dark matter is not an anomaly, as from astrophysics point of view. It's more like a general prediction that you would expect, knowing particle physics, that is possible. It's not.
Sorry, but then you will find all these new states that people hypothetically about have to be leptons because they cannot have strong force interactions, right? Even if
no, this is actually not necessary. They can have strong force interactions. There are papers that explain if you have some additional heavy quarks, but they are very heavy and have a very high binding energy, then they are so small in the size that the cross section can be. Yes, this is still allowed. I mean, it's not like mainstream, but it's still possible. But most likely, yes, you would expect that those states would be weakly interacting or sub-weakly interacting with one another. So at least on a quantitative level, I would say that it's not obvious that dark matter should exist in particle physics, but it's also not surprising that it does exist. Okay, so let me talk a bit about the stability point, because this is actually probably the most crucial one here. So stability, or in other words, who wants to live forever? Out of all those particles, we have like 17 plus 1 graviton out of here. There are apparently elementary particles, and 6 plus 1 would be stable out of this. The lightest quarks would be from energy momentum and electromagnetic charge and biodynamic observation. Electron, energy momentum, and charge actually one of the neutrinos, even though this is actually neutrino, the lightest neutrino would be for the reason of energy momentum plus angular momentum conservation, because it's a diamond, so it could not decay to photons. They are stable just for measuring momentum because they are massless. So forever is out today, they just the time that is infinite, so they can decay. And for the rest they just slots one sweet moment and then decay. So for all of those particles in the standard model, the decay is given by combination of conservation laws, which is the space-time symmetries plus gauge symmetries, something like energy momentum, can be also angular momentums for space-time, and plus some gauge symmetry, or plus some global symmetry. However, the global symmetries are a bit weaker because gravity tends to break them, but numerically nobody knows how strong the breaking is. So those particles can be like proton, very much stable, and voids forever anyway. So this is as good as being stable. But when you form from the elemental particles, you form matter we see. There are other peculiarities, right? For example, as you well know very well, proton is stable, but neutron is not stable outside of the nuclei. And inside of the nuclei is not stable because of the coincidence of standard values of standard Watt parameters. The binding energy, so the electromagnetic coupling is large enough that the binding energy is large enough that the mass difference between proton and neutron doesn't give you enough energy to actually overcome the binding energy. The nuclei, there are more than 3,000 we can know nowadays, and of which only about a few hundred are stable, only 50 are stable theoretically. And atoms are stable because of stability in its constituents and binding energy of electromagnetic interaction. And what about dark matter? So, okay, we can see that stability in the standard model is a non-trivial thing. And then what about dark matter? So, now, something requires dark matter to be completely stable, it can be metastable. But the problem with metastability is that it's a bit weird because it's not enough to have weak couplings or small mass differences. You actually have both and then a very high fine-tuning level typically. Because, so example, neutron has a lifetime of around 15 minutes, even though this mass splitting between neutron and proton is 10⁻³ of the mass of neutron. Right? So it's a very small mass splitting, and even this doesn't allow you to have long lifetimes, like long in terms of cosmology, with the edge of the universe life. If you want to have small couplings, like for example for Higgs mixings, you need the couplings that are much smaller than one standard, which is much smaller coupling that we observed in physics. So it's a bit weird, but this is possible. For example, star neutrinos would have a combination of both small couplings and very small mixing circles and small mass splittings. For gravitinos, the couplings would be very much suppressed because of this gravitational interaction. Or you can have parallel particles, which, by the way, they're also unstable because they elaborate. But then you have stability, and this typically is done by adding some symmetry, which can be either on-top symmetry. Most of the models will have like some Z2, Z3, or global 1 symmetry, which again all suffer from the fact that gravity tends to break them at some level. In fact, if such a symmetry is theoretically motivated, for example, I varied in supersymmetry or P minus L to explain neutrino mass models, for example. Or you can have an accidental symmetry, just like baryon number is accidental in the standard model. So there are models with dark baryon number, or there is a nice observation that if you have a quintuplet of SU2 left, this have an accidental symmetry that makes the lightest state of this quintuplet stable. Just it's a matter of fact in terms of observation of the theory. So one can have this type of theories, and it's actually not hard to write a theory with satisfying this or this, but it's hard to do it in a natural way. So this is for me the main problem for building in some sense, if you want to do it in an elegant way. But on the other hand, then also like some matter, perhaps we don't understand stability that perfectly. So, or at least like we don't have a very good principle why this is stable. So that's that. All right, so let's come to model building. The funny thing about dark matter as a measurement is that we have only one model measured. positive, which is the abundance, and this is to be measured. All the other stuff in the dark matter are limits, and those limits are sometimes very strong, sometimes quite loose, but if you take into account in all the observation requirements for dark matter, that is, it has to be dark, which means no sin, but quantitatively mostly means it's dissipationless. So it doesn't form disks or any compact objects, or compact instances of galaxies. I mean, formally it would be like compact stars if you're but anyway, we have like matter, so it's a source of gravitational potential in the case of matter's cosmological evolution. It has to be cold, that is the amount of rotation equality. It can't have too much of energy dissipation not to explore large scale structure formation. It has to be, as I said, stable, and it's metastable, and it has to be adiabatic, that is the primordial homogeneity has to be the same as other components, otherwise the CTP would work. But even taking all those facts and a very quantitative level in many observations, you still end up with a result that dark matter can be from 10 minus 21 or so levels. So we haven't pinpointed much of the dark matter's possibilities yet. And the landscape of theories is also pretty large. Okay, this part of this series is actually this else, which you asked about what else it could be. You can have modified gravity and some, this is a weird modified inertia. And those theories have their problems, but most of them actually require some dark matter to work. And if they don't require dark matter, there is like one paper now that you can explain it with voltage-like thing. But it actually has a terribly long Lagrangian with very weird properties. And on top of this, this is actually like adding new fields to Lagrangian. So from quantum field theory point of view, you're adding new particles. But particularly like these macroscopic objects, like domain walls, even maybe, okay, this is hard to make part of this, but it was included in the whole landscape. But mostly you have other particle dark matters or wave dark matter, which actually this is the same from quantum mechanical perspective, it's just better to think about this different ways in terms of detection. So mostly for wave would be like light axons, and for particles you have everything from, I'll show an example, but basically I will talk about this for a moment. One of the theoretical requirements for dark matter is that it should be embedded in larger framework, motivated by some other unsolved issues, and predictive. You want to have a model where you actually can measure something. And wish list would be also nice to do like minimal, or elegant or simple, and this is actually not something that we have to have, but from a more sociological point of view, people are trying to satisfy these.
You say percentage, but what it really actually means is falsifiable, because you can predict exactly the same two things between two theories, and then you cannot falsify or distinguish them, right? So it's a subtle difference, but
yeah, so falsifiable would be strong, I would say. Predictive also in the sense that, for example, you would like to have a model where at least practice in some future, you can have parameters that you can predict your dark matter. So, for example, you don't really like models that are dependent on radiative temperature, which you don't know and you're not going to know for. But that's possible, of course, possible that dark matter is not dramatically produced in the early universe, depends on the radiative temperature of alpha, and then you just don't know, and you just have to live with this. Which may be the case of like the dark matter particle, and I will mention in a second, and we're able to measure its properties and point out such a. Okay, so but this is practically not very useful for a person not working in this field. What is a bit more useful is a classification of how it interacts with other model. So it can have gauge interactions. So it can have electromagnetic interaction that doesn't have to be recharged, otherwise you see this. It can have SU2 interactions, weak interactions, and this could be falls in the supersymmetry framework also, but just minimal dark matter. It can work just like models. We add a given multiplier to SU2. And this is going to be perfect fine. And as you asked, SU3 is technically still possible in some special cases of very tightly bound states. Then, if on the other hand your dark matter is not charged by gauge interactions, it can be charged by some photo interaction, which means that the interaction is mediated by a relation particle. But by photo, we mean that the interaction is normalized. And I'll show in a second, and there could be also normalizable interaction types like axioms, neutrinos, and the superstar neutrino have those. And there might be scenario there are none of those. And gravitational, and it's only cosmology that can actually tell us something about that. So gauge interactions are of course the nicest because we can measure them. And they are strong enough that we can measure something in for example, LHC. However, we do know that physics is kind of tends to be always around the corner because it's already 12 years after Higgs boson discovery, and since then there is just desert, nothing else. But as a difference of particle physics here, this discovery was very much expected because, at least the expectation something will be at the energy scale, because we knew that the WW scattering is not unitary, it's just not without the Higgs at high energies. So if you take this scattering, you calculate the probabilities, and take only the electroweak part, the probability will be larger than 1 at some energy. So you need something, and Higgs, for example, was thing that unitarizes this scattering. It could have been something else, but it turned out the Higgs isn't true. And after the Higgs discoveries, this was basically solved, and there was only one quibble left, and this would be the Garden problem, which is why the corrections to the quantum corrections to the mass mass of the Higgs are typically expected to be of the order of the scale of the cutoff scale of theory, which in this case would be very, very large. And therefore, you need to very fine tune what the parameters of the model to actually make the Higgs boson so light, which is possible. And some people claim it's a very serious problem, some people claim it's just explain numbers. This, but nevertheless, historically, it's a fact that it motivated a lot of research on this and experimental ones as well. And one of the research it was partially motivating was supersymmetry. So what people typically think about supersymmetry is that for the older models of the particles of the model, you actually have a super partners, you're doubling the spectrum of particles, and it's kind of funny. But actually, it's a very beautiful mathematical theory that has a very nice features. It's a great simplification of the theory, not of the particle content, but of the theory, because you add more symmetries. And actually, you add more symmetry in such a way that you complete all possible symmetries you can have, as the Coleman-Mandela theorem tells us. It's an elegant solution to the Canadian problem. It's needed by string theory. It produces some sort of a Canadian unification, and it has diagonal candidates for free. Because if you want to have supersymmetric theorem with a proton, stable proton, the easiest way to do it is to impose symmetry that then in the end will mean that the lightest supersymmetric state will be stable. This is kind of bizarre. This may turn out to be a feature in the end if it is found, but we'll have to see. There is not much evidence for succeed these days, so we have to wait and see. But nevertheless, this is kind of a prototype of a theory that is has a very nice framework connected to something completely different, not built to have dark matter at all. I know the dark matter a very possible explanation. I would still say it's probably the best populated framework we have. Yes.
Can I interrupt? Sorry.
Yes, sure.
So you don't consider Susie back the fact that after we found all the Higgs boson mass, the most natural lightest supersymmetric candidate for the dark matter, which is neutralino state, is actually now not cannot be have mass that will give you WIMP miracle anymore. I think.
Right? This is not true.
It's not true.
Yeah, well,
overstated paper.
Yeah, there's a lot of overstated literature in terms of Susie and dark matter, in terms of like how Susie is excluded or like supersymmetric dark matter. The problem is I just first wanted to mention this portals thing because portals are a very common method of design. filtered dark matter. And that's basically three type of portals we have. So you have a visible sector, you have a dark sector, you connect those two. And you can connect this via Higgs portal, which means that you write an interaction term with some mediator field with the Higgs field. You can do it in two different ways. But in this way, this actually can be also dark matter itself, so you don't need a mediator. There's another vector portal where you have a kinetic mixing of some additional dark photons or photons. And we have a neutrino portal where you have some dark matter or a mediator state that connects to white neutrinos, and those then connect to some other other neutrinos. Can be also with composite operators, but this is a different story. And the funny thing is that since you have all these three possibilities, and these three possibilities are very easy to incorporate in the photo model, you can write anything in the dark sector is compatible with observations, and then connect it to start a model and study how much such a model could be detected by this type of interaction, this type of interaction, in a relatively model independent way, such that you can constrain the portal interactions. And then this would apply to many models you can so this is a popular argument these days. So let me say a few things about detection. So okay, this you've seen by the maps, how it goes. There are these three different strongest avenues. You can produce dark matter from standard model, you can collider, you can directly detect the interaction dark matter standard model, or you can look for the indirect detection of annihilation or decays of those states and see the products in telescopes and other observatories. But as Roger was saying, there is a common feeling these days that since we haven't seen dark matter particle, I know in LHC with a plethora of results, but also not in direct detection, no, in indirect detection, that this paradigm is a bit losing attractiveness. But what I want to, I fully understand this, but I want to kind of stress one counterpoint is that this doesn't mean that much actually, because when you look at LHC, there are a lot of kinds in those studies. So you can have like small mass splittings between those states, and they will be perfectly non-visible in LHC. You can have situations where they are obviously just a bit heavier, but supersymmetric, those states are typically looked for in strong interactions or sometimes electroweak interactions. But if electroweak, those limits are much weaker than that. So the limits on the neutrino, which are at this, like if you really think about TeV scale, the limits on neutrino are just from the fact that you have limits on sparks and septums. If those are heavy, which can be in many supersymmetric organizations, down so this is just a lot of points in here. On the detection side, another interesting point is that indeed we probed the elastic scattering cross-section a lot in recent history, but there's no target. You cannot really say that there's no supersymmetry or other WIMP type models predicts cross-sections which are somewhere here. They are perfectly well are here and even much lower than that. So there was completely no, it was more like a completely theoretical prejudice around like wishful thinking that the supersymmetric dark matter has to be somewhere here, it can be well somewhere here. So it is true that there are some signals in the past not very convincing, but nothing very robust. So, but still, this is perfectly possible. And in fact, one can one can draw what is the allowed dimensions in indirect detection, and you can see that if you have a cross section here and possible mass here, with not very much of an assumptions, you can just say that all of this region is actually still fine in observations, and in fact, this line would also give you a WIMP miracle. So if you forget about the prejudices, WIMP is still not even slightly dead. Some take of this kind of a story would be like this: that in 20th centuries, people would say that dark matter is nearly certainly WIMPs, or perhaps access to neutrinos. SUSE is just around the corner, and studying this pure model physics and phenomenology is just the most important thing to do. Now I would say that, at least this, I said that you can hold me up to this, but other people disagree. And that there's no idea of what dark matter really is, and it starts to secure currently. And we have different options. So we can have new detection ideas, which is a great piece of research these days. You can double down and still do the same thing here, and maybe you're going to be right, maybe you'll understand the correct model. But I try to go a different route, which is to make an effort understanding some of the relevant processes these days more carefully, because those studies typically left a lot of holes in terms of like exact physics that's happening. And then having this, maybe either it will be different here, what dark matter can be, or at least at the very least, if when the actual detection comes, we'll be better prepared for understanding what it means for particle physics. And then one last thing about this is that one has to take in mind, remember that even if we detect dark matter particle in the sense of either indirect detection or direct detection, this does not mean we'll know its properties. In order to actually be able to say, for example, what is dark matter mass is, what the particle mass is, or what is the cross section, you would require quite clear measurements from more than one channel. So if you had only, say, only indirect detection signal, like from Fermi-Lat, say, most writers, you would pinpoint your cross section of factor of few uncertainty and the mass more than order of magnitude. And this is assuming you understand astrophysics well enough that you can actually you don't have large uncertainties but if you measure, say, xenon, on the other hand, you can probably you have like maybe not huge uncertainty, but still some uncertainty in mass. But the cross section, in terms of indirect detection cross section, can be very, very different. An only combination of the two gives you some handle, but still not exact. And for signals, so we probably don't expect two signals to come in a very short period of time. So there will be some time before we actually can say something about the quantum, even if there's detection. Okay, and this brings me to last few minutes of production. How much minutes do you have?
We have 5.
Okay, fine. So let me just say, okay, so I work mostly in like production these days, and the idea is like how to, even if when you create a dark matter model, how you would expect is to create how many particles in your way. And there are different ideas of this. I will focus on the thermal ideas, thermal from equilibrium, which is called freeze out, and thermal out of equilibrium, which is called freezing. And okay, let me maybe just explain what freeze out is. So the idea is that it's very early in the universe, dark matter is in full equilibrium, so there's a small universe with dark matter particles starting the particles interact with each other. Then at some point the universe expands and cools down. And so those interactions become rarer and rarer. And at some point when the expansion rate is co-coupled with the annihilation production rate, those will cease to change the number and density of dark matter particles. And this is called freeze out. This is a very simple picture. And what is important in this picture is this process is essentially always present. It's not like we use this to produce dark matter, it's just there. And the only exceptions for this would be if the dark matter is actually not a particle, or it coupled extremely weak to standard model, such as was never in equilibrium, and then we'll think about this freezing part, or we're heating, temperature is much lower than dark matter mass. Then we don't have this process. But otherwise, it's always there. So understanding this process is not only can be used to actually explain dark matter itself, but for example, you could put a constraint on your models. So even if there was like, imagine there was no dark matter in the universe whatsoever, and somebody invented supersymmetry. And then said, okay, proton has to be stable, so let's give it this parity or parity. This model would be allowed by the fact that thermal production will produce matter, which we observe. So you can put limits on particle physics models just from not even trying to explain them, just for the fact that you don't over the universe. And I think, okay, slightly closer with this routing mechanism that's important here. So what is reason on the other hand is that the idea that you have unknown inflation and the physical sector is reheated, while the dark sector is kind of empty or nearly empty, such that the initial inflation doesn't matter much. And then reheating creates a thermal bath, while there is a slow production from this thermal bath to the dark sector by some interactions. And then the expansion happens, the thermal bath expands, but also the dark sector expands separately. And this production, if it happens very early, is typical UV freezing. We'll have this later, it's called infrared freezing. But basically, this is a very old idea. The UV freezing, especially, is the main production for neutrinos, gravitinos, acceros, like from the 60s, or calculating stuff like this. This is typically UV freezing, but the infrared freezing is the idea that you can also have models where you have this photon interaction, and this production is from non-volatile operators, which is crucial because this means it does not depend on radiating temperature. All of that will depend on radiating temperature, while the infrared freezing does not. Okay, and how to connect freeze out and freezing? These are basically kind of mirror processes where in freeze out you start with equilibrium and you decouple, while in freezing you start with basically zero, but you slowly produce and then decouple. While in reality, it's good to remember that both look like this, that the difference is that thermal production means that the coupling is strong enough that you equilibrated, while in freezing it was not strong enough. But from reheating, you basically expect such a picture. Okay.
Star also.
Sorry?
Dark matter. Home star.
The stars, dark matter. So normal models, no. In some specific cases, yes. So for example, you can have axion stars. You can have models of normally the problem is that in order to form star, you need to have a gas that collapses. In order for it to collapse, you need to lose energy efficiently. You need to dissipate. And dark matter is, from all the observation we have, dissipationless. There can be some dissipation, but it cannot be strong enough as the one that allows you to have a French-like emission of a photon and then collapsing. So in order for dark matter to produce like really compact objects, you have a very specific model.
But you can collapse gravitationally freely.
Right, but this is not good enough to form. Okay, so maybe let me okay, so using last 2 minutes, I just want to say one of the things that we're working on, which is I told the story of dark matter simple equilibrium and then chemical decouples and freeze out. But there's one more player in the game, which is the kinetic decoupling of dark matter. And this is so chemical decoupling tells you about the number density, kinetic decoupling on energy of dark matter fluid. And if you want to solve this carefully, you need to solve the Boltzmann equation, which is what people do. But what is that take this Boltzmann equation and integrate over momentum to get the number density equation. And this is the thing that is all the numerical codes on the market. And you get the standard freeze out picture. But in fact, you can do it only if you assume that at the freeze out you have a kinetic equilibrium. And those is the assumption it holds. And what we worked on is what to do if this assumption is incorrect. And in fact, there are cases where it is incorrect. And we developed a method to deal with situations where this is not correct. So, for example, you can have a situation where you have resonant correlations, or a situation where you have multi-component dark sectors, and so one of the dark particles in the dark sector decays, for example, to the other one, and this means that it injects also energy and disrupts kinetic equilibrium. And for take this into account, we published a code called Break, which we hope will be a standard tool to calculate this situation, to calculate Break abundance in the situations where you cannot really guarantee kinetic equilibrium. Okay, maybe this is on the bottom. Just want to say that one example maybe. So I mentioned that you have some other state decaying to dark matter, and it will distort equilibrium. And so it has a very nice feature, for example, that imagine you have such a picture that times go on, you have number density, and you have just standard dark matter freeze out nothing really interesting happens. On top of this, you add some unstable non-linear state, which decays to dark matter. So there's a lot of it, and then it decays to zero. So what do you expect for dark matter to happen? You would expect it would be more of it, because some of those states will decay to dark matter. Then you say, okay, you have more states, so the relation will be a bit stronger, so maybe not as much as you'd expect in the first place. But if you take into account the fact that the kinetic equilibrium doesn't have to be maintained, you can have also this situation that actually adding more dark matter particles in their universe will make the final abundance. And this can happen, as Victoria explained like this, that you have your first population of dark matter particles, you inject some energetic additional dark matter particles. If you assume that they will kinetic equilibrate, you will end up with more dark matter, nothing really happens. But if you actually take into account the fact that the kinetic equilibrium is not maintained, then you can see that some of those particles will hit the particles of low energy, and then they might have enough energy to become a threshold of annihilation and increase the annihilation rate quite significantly. And you can do it with some scattering as well. You have a bit different picture because those scatterings will reshape the distribution again a bit. And in reality, you indeed, okay, this is the same picture I showed, but in actual computation. And you can see that the distribution function, the yellow thermal one, is actually very much non-thermal if you take into account. So we are looking at this type of systems and trying to understand this more in a case where this turns out to be very important, because as you might suggest that models of this type are present, this will be prepared. Okay, and this is, let me stop here, let me just go to conclusions. Okay, so my conclusion will be like this. Dark matter is actually a welcome guest. I would say it's not that much unexpected, at least as a part of the theory. Perhaps the fact that it's so much of it is a bit unexpected, but in fact can be useful hint for discovering beyond thermal physics. And for the second part, I just want to advocate that this kinetic equilibrium assumption, which is always made, is not good enough, and we are working to make it in a way which is as simple as possible, but not simple. Thank you very much.
Are they bosons or fermions?
There we go. Fermions are not natural. Maxims, for example. In fact, there is one big difference between fermions and bosons is that you cannot go to light with fermions because of the Pauli properties. So if you had like enough of dark matter to explain cosmology, then you cannot put too much. If it's too light, you have too large number density at a given volume, which you cannot do. And bosons you can go to 10 to the minus 22 roughly, which is the size below which you would have the point function large enough to forecast.
Yes, that's on the distance between.
Yes. So, but most likely, I mean, we know that all the matter we have are fermions and fractions of bosons, so natural to expect it. So.
Any other questions?
Thank you very much for a very nice review and very well balanced talk. We enjoyed that. So my question is touching a little bit what Andrzej said. Of course, like matter can evolve, but they won't have the same annihilation chance, right? So in your Drake example, you added the complexity that basically the new particles that are not kinematically in equilibrium can heat up the non-adhesive dark matter and make it more susceptible to annihilation. But this is like for Majorana fermions, right?
No, this can be for, I mean, for example, the first model we looked for in Drake actually was the model which is sometimes called the simplest dark matter model you can think of, which is the scalar signal.
No, just
If you take the scalar signal model, which means you have scalar model plus one scalar state. And the funny thing with this model is that it's actually mostly ruled out, but not completely, because there is resonance region. This resonance region is still allowed. Everything else is ruled out, at least if you want to have thermal production. But if you look and the fact is, the resonance basically means that the annihilation process is resonantly enhanced, but the elastic scattering process is not. So you cannot guarantee chaotic equilibrium. And if you look on this plot, you can see that the ratio of our computation to the standard computation in some mass range close to the resonance, but not on top directly, can be as different as order of magnitude.
Thanks for clarification. Well, my actual question is to try to encourage you a bit to go to speculation. You don't like, but let me give as a particle physics expert here. You said the nightmare scenario is that the dark matter doesn't interact anything by gravity. But would you consider as another nightmare scenario that people usually assume, unless you use Occam ratios and only assume one kind of particle, dark matter, but there can be many stable states that are dark. They can even have some interactions, and this would make all our astrophysical simple models that always assume one model much less constraining. So can you say something about that?
What I find unlikely in this case is that you would have a lot. I mean, I think it's quite possible there are a lot of stable states, but I think it's unlikely that those states will be abundant in a similar way, or like typically one will dominate. So cosmology will, at least current present accuracy, will probably taking the dominant one. It's really, for example, from thermal production, it's really unlikely that you have two states which have basically 50-50%. Yeah, so it's possible, but I mean, like it's not a model. You have some abundance of electrons and protons from, and then neutrinos, but neutrinos are completely done.
Yes, I'm not working in this field, so maybe it's a totally stupid question, but from observations, you know the radial profile of the dark matter halo. So this profile is only resulting from gravitational interaction.
Yes.
And so there is no traces whatsoever of other interaction.
Unless the other interactions were very strong. Right? So there are the self-interacting dark matter models, which I believe you had the colloquium university about this. So if I can come as we talk about this, if you have self-interaction dark matter which are at the level of close to being excluded by observations, but okay, still perfectly allowed, then you would indeed have situations where your profile and your whole evolution of halo formation can be different and significant. But to be kind of fair, in order to have such large interactions, those are interactions of the nuclear particle, like between proton and proton. So the elastic scattering cross section has to be very large, and this is not what typically happens in theoretically motivated high energy physics models. So supersymmetry, for example, no way. Interactions are too small. But there are ways of doing this. So, for example, there was a couple of years ago, there was this observation of Hubble cluster, one Hubble clusters, when there was apparently some evidence of the fact that dark matter dragged. So there was some drag of dark matter component in the collision of coaxial clusters, and this was interpreted as scattering cross section. But then I think it turned out that this was the measurements changed a bit, and this disappeared.
Because also existence of the satellite galaxies, which confirm dark materials cannot evaporate when it becomes subhalos too much. So this all adds up, right? But Martina, you're very enthusiastic by saying that we observe a range of the it's not observed, it's like,
Well, some constraints.
you have some constraints, but not the proper observation.
Very simple question. You were showing some images from Faraday, for instance, supposing we would get this type of constraints. And I'm curious about, how much those constraints depend on a specific model when you put this on. Because they have to have some annihilation, some abundances in there.
Yeah. So, okay.
Yes.
This was, of course, done in a kind of other round. So you, as you can model, you produce a signal, and then you say, okay, if I detected such a signal, how much within this model I can reconstruct the properties thereof. But this is not as much model independent as your thing, which is on one side good for the detection effort, but it's actually bad, as I said here, because if you have a signal, like if let me would give you like a mass cross-section and elevation channel information. We'll be only thinking of it. And from this itself is not very easy to say given how many models you have to say which one is true. That's why the best thing would be to have a signal. This is much more. And of course, you could have some.
I think we can end the speaker. Thank you very much.